Swayam Prabha. Digital India. Educated India.
Good morning, everybody. We are in module 2, where we are trying to discuss production of medium, high and ultra high vacuum. It contains several pumps like rotary, diffusion, roots blowers and dry membrane pumps, water ring pumps, steam jet ejectors, turbomolecular pumps, cryo pumps and variety of pumps for various ranges of vacuum. In that process, we have already completed rotary vane pump, which is most popular pump for vacuum technology, because it is the backing pump for several other high vacuum pumps. It is also a good pump by itself to produce a vacuum of the range of 10⁻², where 99.99% of the gas has already been removed. But unfortunately, for our day-to-day life, most of the applications in electronics, nuclear engineering, space technology, molecular distillation, TV tube technology, display technologies, metallurgical processes, refining in a high level, high tech level rather, we require 10⁻⁵, 6, 10⁻10 torr also in particle accelerators. So, naturally, it is not good enough if you remove 99.99%. You should also remove 99.999999. Then only you will have electronics, nuclear engineering, space technology and metallurgy, etc., X-ray tubes, medical applications and all. This I already explained you in the first module, but just I want to understand why we are going for a diffusion pump when 99.99 is removed by rotary. No, it is only the last few molecules which are there. If you are removing further to a very low molecular density, then only you will have very good applications. These ranges are called high vacuum up to 10⁻⁶, starting from -3. Beyond that, it is called ultra high vacuum. In various applications, we will come to know later how or why this high R is required or ultra high is required and which pump to be used. That comes under selection criteria. But right now, we are in production game. So, let us understand all the pumps one by one, what is its working principle, limitations, etc., because we cannot understand everything in one shot. So, today we will be discussing the action and construction of a typical diffusion pump, which is a molecular pump by itself, which can produce a vacuum of the order of 10⁻⁷ torr with the help of a backing rotary pump or a combination of rotary and roots blower, which I will also discuss little later, which is also a very important pump. That way, diffusion pump with a combination of rotary has become very popular in the initial days of vacuum technology. It is only last 30-40 years these turbomolecular pump, cryo pump and other pumps have come into existence. So, for a long time, over a period of 70 to 80 years, diffusion pump is the only working horse which can produce high and ultra high vacuum. Whether it was a metallurgical application or space or nuclear or electronic applications or anything that you see, it is possible only because of diffusion pump. And even today, for very large metallurgical applications or very large simulation chambers, etc., people still use diffusion pumps. The reason why they use other pumps of turbo pump, etc., we will come to know later, mainly because of contaminations, etc. But quantity wise, this can also produce same amount of vacuum which other high tech pumps and costly pumps can produce. So, diffusion pump is a cheap, well established technology to produce very good vacuum, good enough for most of the applications, where you do not mind the chemical composition, the chemical impurity effects, then it is good enough for the application. So, it is a very important pump like a rotary pump. Why I am giving so much introduction is, this pump was responsible for most of the technologies in the last century. It is the first half is totally dominated by the diffusion pump and rotary pump. So, in this the concepts that are going to be covered are the introduction to this pump, the construction and operating principle. As I told you, any pump if you want to understand, first you try to understand construction without putting your brain how about action and principles, etc. Okay. Then we will see the operating principles. Afterwards, we will see various materials in diffusion pump. Most of the materials, constructive materials, we know stainless steel and other things, that we will see later also more in detail. But the main component of diffusion pump is the diffusion pump fluid, which is a very costly thing. It is not like a lubricating fluid that we are using in rotary vane pump. So, those things we will see a little bit from the physics and chemistry point of view, and later we will see from the process point of view how this diffusion pump along with the help of rotary pump is going to produce very good vacuum, which is in the range of high and ultra high vacuum, that is under pumping performance characteristics. The end we will see what are the limitations, if there are some special points to be considered while selecting this pump for an application, or if there are any criticalities that we need to maintain, is there anything that we need to take care while operating this pump. So, this type of precautions and how much is the electrical power requirement. So, all these things we need to understand little bit. Time, in a limited time it may be difficult, as I already crossed quite a good amount of time in introducing, but it is required. Later you can get these things from various books and manuals and in net also. So, look at the diffusion pump like a layman. First, a construction. You will see here a small cylindrical structure, cylinder sealed at this point, and bottom there is an electric heater, and nobody should touch that electric heater. There is a small shield to that, and this shield also will act like a radiation shield, so that heat is not transferred to the surrounding. It is fully utilized for heating the fluid, and inside this bottom of the cylinder we pour that black looking thing is the diffusion pump fluid, and into which we introduce a 3-story type or 4-story type of a jet assembly. Several people call it with different names, and this type of jet, you see it looks like this. The jet is shown here and the cylinder is shown here. These are the actual figures I have taken from labeled manual, and this is very well established pump by itself. So, this jet is not vacuum tight or anything, because it is within the chamber, it is kept like this. So, a cylindrical container, a jet assembly, a heater, a radiation shield, and to this cylinder there is a chilled water supply, water cooling coil, which is cooling. So, you are heating in the bottom, you are cooling in the top. So, oil gets evaporated, these arrows, solid arrows are vapor molecules of this liquid, and they jet out, because that is the only opening they come out, like an umbrella. This is one umbrella, this is second umbrella, third umbrella, like that, and they touch this surface and get cooled by this chilled water and condense back into oil, and that oil will glide down or slide down slowly into the bottom, and again it gets heated and again evaporates. So, heating, evaporation, coming out with a high speed and touching this, getting again condensed and joining the boiler again with the help of heating and cooling. Cooling is supplied by chilled water, heating is supplied by the electric heater. But all this is going on in a vacuum condition in this entire container, created by a side coupling connected to a rotary pump, which I am not showing here, and that pump I popularly call it as 4 vacuum pump. That means, it is trying to evacuate this container before you switch on this electrical heating. it was just a chamber, that is all at that time. These so solid aero molecules are not there because it was at room temperature and it is like a liquid, that is all, it is a fluid, heater is off. So, at those conditions there is a vacuum created. These dotted molecules, they are always there in a rarefied manner depending on the pressure. These are actual gas molecules inside your process chamber which you want to remove. That is the purpose of evacuating the chamber. Where is our chamber? By the way, since we are discussing about pumps, I am not showing the chamber, but this port in the top of it with these flanges, it is connected to the chamber. That I have not shown here. Later in the applications we will show one by one. So, that chamber, whatever be the molecules, were originally removed by this pump, rotary pump, when the diffusion pump is not yet acting like a diffusion pump, and all the molecules are rarefied to 10 power minus 2 torr. Under those conditions, when you switch on this electrical heater, there will be a pressure rise inside this chimney to a level of 0.8 or 1 torr, depending on this temperature, which is around 200 to 250 degrees centigrade. And when it comes out, it is coming from this 2 torr up to the 10 power minus 2 torr created already by the rotary vane pump. So, there is a huge pressure drop across this nozzle exit. So, pressure energy will be instantly converted into velocity energy, and it is so high that it will form a supersonic jet. Its velocity is higher than the sound velocity, and it touches that valve and gets condensed and becomes oil again, and we have to see to that the vapor pressure of this condensed oil is not much, otherwise it will be spoiling instead of producing vacuum, that we will see later. And while coming this axis, these molecules have got two components, one is x component momentum, its mass into velocity, and y component momentum. While x component momentum is taking them towards this wall where it gets condensed by the chilled water, y component can be used for baffling these freely floating molecules which are oxygen, nitrogen, etc., which were there in the chamber, which could not be removed by the rotary pump initially, because at 10 power minus 2 torr pumping speed, rotary pump's pumping speed is 0 almost. So, there will be some residual molecules which are now here, and they are molecules, they are not gases, because the mean free path is much more compared to the wall dimensions. So, each molecule will act like a free molecule. So, molecules will be moving around all the chamber, and sometimes they enter into the throat of this diffusion pump, like that. At that condition, when you are switching on heater, these heavy molecules which are oil molecules, whose molecular weight may be 500, 600 compared to the molecular weights of these gas molecules which are only 28, 32, like that. So, they will hit them and baffle them down. So, while doing that, more and more molecules may be arriving, not because of pressure drop, because pressure drop has got meaning only in gases when there is a viscous drag. Pressure drop is no more the driving force for molecules to go from one side to the other side. Okay. So, molecules are going in every direction, free molecules, but if the pressure drop, it so happened, then that low pressure side molecular density will be less, high pressure side molecular density will be more. So, when this flux towards that low density is more, and the return flux, those molecules also will come left to right, but those molecular flux will be less. Net effect will be as if some molecules are moving from the high pressure side to the low pressure side. This sort of picture you have to understand in molecular flow. We will discuss this again when we are discussing in detail conductance concepts. So, right now you imagine the gas has been already evacuated, air has been, in our case air has been evacuated to rotary pump to a level, the now gas is started behaving like molecules, and the chamber, diffusion pump chamber along with jet and all also is evacuated by the same backing pump, as well as the main chamber in which you are doing some application, whether it is a thin film or electronic. If so, what is going to happen now finally? These molecules, when they come out with heavy molecules, they are like strikers, and these the air molecules are like coins, because their molecular weight is small. So, their y momentum of these oil molecules which are coming out, they can be utilized to baffle them down. So, it is basically molecules are tapped down, they are given, they are entrained inside this jet and afterwards they are baffled down. But it looks like as if molecules are entering here and within this high supersonic jet column type thing, they are diffusing. This is a dense phase and molecules, air molecules are low phase, as if they are diffusing down and afterwards they are baffled down to the annular volume here, which is isolated by this high speed supersonic jet. If you look at from the top, it will look like a umbrella and this jet will act like a dam. So that this side of this dam is isolated from that side of the dam. So, molecules will only get hit and come down, but they cannot go back again. So, slowly molecules which are coming from all the way from chamber any direction, it so happens some molecules will enter here and they will be baffled down and they cannot go back. They will be applying, they will getting a little higher pressure now. Afterwards, they will enter into the second jet and third jet. So, progressively these molecules will, from a 10 power minus 2 tar initially, they will be slowly getting compressed. Under compression, now the rotary pump which it could not evacuate initially the same molecules because it was minus 2 tar, now they have been compressed by these bullets, by these oil molecules which are acting like molecular pistons. So, they are making down, there is a piston type of equivalent picture now. So, so many molecules are hitting them and they are not allowing them to go back and they get compressed, crowded and pressure increases. At that pressure, there is a finite pumping speed for the rotary pump, it gets down. So, this is a continuous process going on in the diffusion pump. So, what are the components? Water cooling and all these things are written here. You try to read out at your leisure and you can always contact me. We will have quiz and many other things later. Right now, this much introduction is good enough. You try to read any book to understand the working principle. So, in few sentences if you want to tell, the oil molecules are heated in a pre-evacuated container, cylindrical container. They go through the top of the chimney, they come out like a supersonic jet, they condensed by a water cooling thing and they come down. This type of fountain principle is creating a supersonic jet of high molecular weight of oil molecules. They will hit the otherwise free molecules which are moving around with 10 power minus 2 tar originally created by the rotary pump. They will be baffled down because molecule can compress molecule, no piston or mechanical things can compress. Okay. So, it is not like compression expansion principle, they are basically baffled them down. The molecular momentum transfer is going on there and this way they get compressed. So, we have to take necessary precautions of maintaining say low vapor pressure here and also molecules are properly contained. All the molecules may not go, some oil molecule may go back, we will see in the next few slides. So, these are various hydrocarbons which are being used in diffusion pump for producing high vacuum conditions. Like they are having ultimate pressure that can be created with various types of hydrocarbon oils as siloxane oils. These are all commercially available. They are much more costlier compared to the lubricating oils that we are using in mechanical pumps. There the oil purpose is sealant, coolant and lubricant. But here the purpose is the very diffusion action itself is based on this special quality oil. These oils will evaporate, they produce molecular pistons and they will make the air molecules which could not be removed earlier by rotary pump to come down and these molecules crowded in the bottom side of the diffusion pump, they will not be able to go back because of the dam that is created in the supersonic jet assembly as we see from the top and slowly minus 2, minus 3, minus 4, minus 5, minus 6 like that density, they will get various levels of vacuum. So, these are the various fluids. If you see very costly fluids compared to that, a typical lubricating oil may be coming to 30-40 rupees, but this may be costing around 30,000 rupees sometimes, very good quality oils or 20,000 rupees. So, they have got special properties. With little bit of increase in temperature, they should create enough pressure to go up through the chimney and again when it cools down, it should come to very low vapor pressure, so that it will not interfere with your process vacuum, etc. Because of lack of time, I will not be able to go into physics and chemistry of it, but it is very interesting. It has been developed over a period of 100 years. I cannot cover in 20 minutes. If you can see these books in Wikipedia, you will get beautiful stories behind it. So, what is the pumping performance? Pumping performance means we have already explained pumping speed. Pumping speed itself is a function of pressure, I told you in the rotary vane pump. Same thing here also. In rotary vane pump, it starts from maximum and falls down 0. But in diffusion vacuum pump, it starts from a lower value, peaks up and again falls, because at higher pressures diffusion pump will not work, and if you forcibly work on these silicon oils, it will become silicon dioxide, and charred oils, they are of no use, they will not behave like diffusion pump. You will not get molecular actions or molecular beaming, molecular type of momentum transfer, etc. So, you require a pre-evacuation. That is why the figure very clearly shows you have a pumping speed effectively down in the higher side, where it depends on the backing pump chosen, and later pumping fluid slowly picks up. It is linearly it is picking up. So, this is a pressure in torr, pumping speed, relative units we are plotting here, and afterwards there is a constant pumping speed region, and at the extreme side, just like rotary pump falls down, no pump can produce 10 power minus infinity. Somewhere or other there will be limitations. What are those limitations? We will see the vapor pressure of the oil itself, and sometimes it may not be able to catch, there will be a lot of leaks, and there will be some chemical effects, physical effects, and for every pump there will be some limitations. So, slowly that will be ultimate vacuum limitation is the first region, constant speed is the second region, constant throughput. Why constant throughput? Because it is a linear thing, y axis is pumping speed, x axis is P. Pumping speed into pressure is the throughput. So, by any linear curve, the product is constant S into P. So, it can be considered as a constant throughput. Afterwards, it gets overloaded, and it is because the things are not able to immediately taken by the backing pump, depending on the backing pump capabilities, because the diffusion pump only knows them and push them into bottom. Now, rotary pump has to take over like a relay race. If it is unable to take, sometimes what happens is pressure gets developed, then densities will be too high, that will be critical pressure at which these dams will be punctured, and entire thing will come to the same pressure. That time totally it will be spoiled diffusion pump. So, we have to maintain whatever that is coming out, it should be immediately removed by the backing pump. That we will see later, a critical backing pressure has to be maintained at this pressure level by the backing pump, 4 vacuum pump, the mechanical pump which is acting like that. So, we have to match the throughput, the pumping speed at the diffusion pump top multiplied by the vacuum level S1 P1 should be same as S2 P2, because throughput is the proportional thing to mass, that should be conserved. At low volumetric things are not conserved, but mass is conserved always. So, S1 P1 above the diffusion pump should be same as S2 P2. Accordingly, you have to choose the matching rotary pumps. Okay. So, next slide, same pumping speeds. Suppose you are evacuating only hydrogen, like in space technology or something, you are evacuating only argon, some inert gas atmosphere, etc., only nitrogen or only helium in nuclear fusion industry or nuclear other industries or space technology cells, then the coin sizes are less and less. So, smaller the coin, the momentum transfer by the oil molecule to them to baffle them down will be better. So, pumping speed will be better for the lighter molecules, but lighter molecules also know escaping again back. So, ultimate vacuum is poor, but pumping speed within the allowed range is high. So, what I am saying here is lighter the gas, pumping speed is relatively high with respect to heavier molecules, but ultimate vacuum is relatively poor. Okay? And that pumping speed expression is given by this. I will not go into the details. It is proportional to area of the pump, because molecules have to enter first, and whatever is entering, whether it is -3 or -7, the diffusion pump molecules are sufficient, they will be able to remove them with a factor. So, with a constant factor, the pumping speed will be constant. Pumping speed constant means 10 power minus 3 torr. If 1 lakh molecules come, all 1 lakh molecules are removed, and if 1 lakh molecules are there for unit volume, then 1 unit volume has been removed. At 10 power minus 6 torr, only 1000 molecules are there per unit volume, all 1000 molecules are removed. That way, a 10 power minus 6 star if you remove 1000 molecules, a 10 power minus 3 star if you remove 10 lakh molecules, both are same with respect to pumping speed, because density is high anyway. So, if in terms of volumetric units, because the unit of pumping speed is liters per minute, that is the reason you get constant pumping speed. This concept you have to little understand, because many people who are operating diffusion pumps, many people who design, they may not understand why constant. 10 power minus 3, 10 power, what is being constant? It is only volumetric pumping speed that is constant, not the mass. Here, the pumping speed multiplied with the pressure is much less compared to this. So, number of molecules it is pumping is much less here compared to this, but pumping speed is constant, because less molecules per unit volume at 10 power minus 6 star is same as more molecules for the same volume, and when you are talking volumetric units, it will be constant pumping. Okay. So, throughput when you do that is conserved again. So, this has been explained. Again, when we go to ultra high vacuum pumps, we will come back to these concepts, because concepts are certain things which you have to discuss again and again. For the present, if you think it is proportional to area of the catchment area of the diffusion pump top flange and multiplied by a Ho factor, because all the molecules which come, some of them may go back. It does not know that it has to hit these oil molecules and go down. So, probabilities come into picture. These high vacuum pumps work on probabilities. That is why this RT by 2 pi m, these are all Maxwell-Boltzmann statistics related things. Okay. It is not like viscous rho v d by mu and all these viscous drags. If you drag some molecule, it will drag. All that concepts cannot be applied once you cross 10 power minus 2 tar. Molecules are travelling on their own. It does not know that there is a pump from the chamber and that is creating good vacuum. I want to go there. No, nobody to know. It does not know. It so happen it will go all the directions, but this direction whatever goes is caught by the molecule. So, return journey is not there, but forward journey is not accelerated, but in viscous flow in the rotary pumps, when you try to suck, that is why it is called suction, but in high vacuum side it is only pumping, molecular pumping. So, all the pumps of high vacuum, whether it is a diffusion or turbomolecular cryopump, these are all called molecular pumps, they do not pump gas pump, whereas rotary pump is a gas pump initially at minus 2 tar and all, little bit of transition region is there, some bit of gas behavior and molecular behavior will be there. But after that it is purely molecular behavior. So, we are not removing we are removing gas molecules for high vacuum, and this is the basis for all modern day technologies. If you do not do that, catching molecules by molecular things, this is we are catching molecules by molecules, oil molecules are catching the gas molecules. So, this sort of phenomena you have to understand in vacuum technology. So, it is a beautiful field. Mechanical engineers with a little bit of physics knowledge and chemistry can do lot of startups to develop all these pumps and fluids and start making semiconductor industry, space technologies, certain things you can supply to ISRO and other people and DAE organizations and all. Lots of things are to be developed in India for vacuum technology, whether it is a production or measurement or troubleshooting or various types of designs. So, you have to understand the physics and chemistry at molecular level. Okay. This I have already explained you. In the back side, if the pressure is too high in the diffusion pump, this is the chamber. Now, I am showing a chamber in the diffusion pump. If the pressure is too high, it will puncture this supersonic dam, and once it is punctured, it is the same volume, it is a connected volume. So, suddenly high vacuum 10 power minus 5 tar or minus 6 tar created by this ionization gas P2 and P1 is only 10 power minus 1 tar or minus 2 tar. Initially, this only was evacuating this, now it is evacuating with the help of a diffusion pump. So, you may think that rotary pump is taking the help of the diffusion pump to compress it from 10 power minus 6 to minus 2, afterwards it is able to take. But other way also, diffusion pump is compressing and giving it to rotary pump, it cannot exhaust it to atmosphere. So, diffusion pump takes the help of rotary pump in order to exhaust it to finally atmosphere. Finally, every molecule has to go to the atmosphere, then only we have removed the molecules. So, from this duty relay race, this will be taken care by the rotary, from minus 6 to minus 3 compression is taken care. In the process, if it is not matching properly S1 P1 and S2 P2, then what happens, pressure increases, a critical pressure, and suddenly it will take off, and the above pressure P2 also 1 millibar and P1 is also 1 millibar, then entire application is out. Several times I have offered courses in several companies where they got into these troubles in vacuum interrupters, manufacturing, electronic industries, capacitor making, etc. They were having this type of troubles. So, we had solved those troubles by properly matching these matching pumps to rotary, diffusion, etc. So, criteria is you should see to that the backing pressure never crosses the critical backing pressure even under loading conditions. Metallurgical furnaces, it is not only evacuating the chamber during melting, thin film depositions, it will evacuate those extra molecules also. We have to maintain that vacuum level, and certain molecules during the loading conditions also have to be removed. At that time there will be fluctuations here, but you should be able to handle rotary pump. So, all these things you have to take in the vacuum system design. Well, we are discussing system design with for various pumps and various chambers and various applications. That time we will come back to these concepts, but right now you should know that we should maintain a critical backing pressure. And this also I have told you, diffusion pump molecules which they have come out, some of the oil molecules, instead of doing their action of compressing the gas molecules, they may get deflected back and they may not be able to condense here because of cooling for some reason. Most of the oil molecules will condense and form a liquid and come down by gravity and again join in the pool of the boiler and again go up, but some fraction may go back. That is called back streaming, and back streaming is dangerous because your composition of a thin films or CVD or PVD or whatever applications in metallurgy, you do not want water, you do not want hydrocarbons because they are contaminating your entire ambience. So, instead of getting P types or N type, you will start getting some other hydrocarbons will be interfering with your silicon processing or other semiconductor processing or in molecular distillation or even food processing. Though pressure is high, they will not allow even ppm level any other oily things. Even slightest oily things in a food, you can imagine you do not feel like eating. So, thus such things you have to see to that this back streaming of oil back into the chamber should be avoided. How do you do that? By creating a water cooled baffles which are called chevron baffles, and their liquid nitrogen cooled baffles, so that even if they go back, these water cooled baffles will baffle them down, and liquid nitrogen cooled baffles even they condense this oil totally into liquid and solid state, so that they do not go all the way into the system and contaminate that. So, this type of baffles and cold traps are very important to avoid back streaming. In the internet you can read these back streaming concepts, and only after these cryogenic techniques have been developed with liquid nitrogen trap, the diffusion pump oils could be successfully deployed for analytical instruments like XPS, M, etc. to go to 10 power minus 9 tar, minus 8 tar without any cross contamination of this hydrocarbon signal of diffusion pump oil into your main signals, particularly when you are studying interfaces or biomolecules, etc. So, these are very important. For lack of time, it will not be possible for me to thoroughly explain these limitations, but you can easily read it later. When you come to the system design or purity, etc., we will again touch upon these points later. Right now, we are only discussing it as a pump. So, finally, this is the typical high vacuum pumping system containing diffusion pump, cold traps and main isolation valve. If you open only, diffusion pump is connected, and it is connected back by the rotary pump. This is called backing line, and there is a valve here called backing valve. Sometimes you need to close this and you need to close this, then the entire diffusion pump is isolated from the rest of the world, and you can use this rotary pump to evacuate through this roughing line with a roughing valve directly from atmosphere, because every chamber to start with was atmosphere. So, if you directly connect it to the hot condition, the oxygen, the silicon oil will get spoiled. Silicon based diffusion pump will not work at a hot atmospheric pressure. So, it is equally important to evacuate the chamber to 10 power minus 2 tar before you even prepare the diffusion pump. But at times in the batch processes, it is already in prepared conditions, so you may not be able to cool it again. In such conditions, this main isolation valve and backing valve are closed. These are called backing valves because it is connected in the backing line, and this is called backing line because the rotary pump is backing the diffusion pump to take off, and in the relay race it is able to take those molecules further finally to exhaust to the atmosphere. But same pump can be used in the roughing line, and during that time these two valves will be closed. So, roughing mode, backing valve and main isolation valve to be closed and roughing valve is open. After you reach sufficient low vacuum, low pressure, high vacuum, 10 power minus 2 torque, where rotary cannot produce better. Then you close this valve, then open this valve, then open this valve, then the same chamber is exposed in this route. Now you will start getting minus 6 torque. Same thing is shown in a figure in our laboratory. It is there. It is a induction, it is a hot press. There are induction melting furnaces also in our laboratory. All of them are metallurgical applications. They are connected through the main operating valve here, L valve, and this is the diffusion pump that we are discussing, and it is connected to this rotary pump as a backing line. So there will be backing port like this bottom, and there will be roughing port which is bypassing the diffusion pump like that. You can see all those things here, and in between you are seeing something else which is not normally connected in the laboratory scale. It is called booster. It is a roots blower, which we will discuss in the next class. It is required in matching this effective backing pumping speed sometimes, because huge amount of metallurgical applications, huge amount of load if it comes, rotary pump matching if it is not there during particular time, you may have to boost the rotary pump pumping speed by a booster to match the diffusion pump backing port here. If the pressure is suddenly high, then if it reaches critical, entire thing will be spoiled. Instead of getting vacuum, we are spoiling the product. At that time, if the roots blower is connected here somewhere, which I have not shown here, that will be boosted always, and that can be bypassed if you do not require when there is not much loading, and it can be connected in line like that, etc. So, these booster pumps in the same diffusion pump action we can further discuss in the system design, but for that apart from rotary pump and diffusion pump which you have completed so far, we also need to discuss roots blower, which we will take up in the next class. Thank you very much.